everyone for joining us for another SEM Talk. This is, I believe, our 6th SEM Talk. And if you haven't been to one before, it's a new series we created where we've asked faculty and staff at SEM to provide our alumni, our other faculty and other staff, and our parents and our students with just, talks about things that they're passionate about. So tonight I'm excited that we will be talking about the STEM program at SEM, and this will be led by John Idem Jr. John is a 1990 graduate of Wyoming Seminary and has been a member of the full year faculty since 2010. John currently serves as director of the Lewis Maslow STEM School and teaches 5th grade science. As part of the summer at SEM program, John also directs STEM explorations at the lower school and the English Language Institute Summer STEM. As STEM director, John strives to inspire STEM thinking, creativity, and innovation through dynamic learning experiences. Dedicated to integrating STEM into the arts and humanities, he's an advocate for helping students develop the right skills to become critical thinkers and problem solvers through interdisciplinary opportunities. In his spare time, he enjoys spending time with family, carpentry, and serving as a community volunteer firefighter. And so now I would like to introduce John. So I will remove the spotlight from myself. I'm going to ask you to unmute and spotlight you. John?
Okay, thank you.
You're welcome.
Let me go to share my screen as well. While I'm doing that, let me just say thank you for hosting us. We're delighted to be a part of tonight's presentation. Okay, so I am John Idem Jr. I am the director of the Maslow STEM School. I'm joined by associate directors, Jill Carrick, who is the lower school science chair, as well as Jim Doherty with the upper school math department, and Dr. Andrea Nerozzi, who is part of the upper school science department. And Dr. Nerozzi will be sharing some information with us about one of the programs that is part of our STEM program, the Science Research Group, that will come later on in the presentation. So I'd like to start out by telling you a little bit about the history of the STEM program at SEM. I'll also speak to some of the STEM-based programming and learning that we do, as well as a new academic concentration program that we're very pleased to be launching this year. And then once we're finished with that, we'll hand it over to the students to talk a little bit about some of the projects that they've been working on. And then we'll wrap up tonight's presentation with a presentation by Dr. Nerozzi with some information about the Science Research Group. Of course, then we'll be delighted to answer any questions that you have from there. So some of the history. In 2007, Dr. Nygren joined us as president. And Dr. Nygren had an extensive history in engineering and education and joined us, and together with the board of directors, determined that we really needed to work to make Wyoming Seminary an educational leader in STEM. And so that led to the development of and the founding of the Lewis Maslow STEM School in 2012. At that time, Mrs. Rachel Bartran became the first director. Also in that year, we designed and implemented the Lower School Innovation Center, sponsored by the Caroline and Kenneth Taylor Foundation. And then we also introduced the STEM lecture series that spanned both campuses for various events. In 2013, the first STEM courses were offered at the upper school, as well as STEM-tastic Saturdays were introduced. In 2016, I took over as the director of the program. We developed a new leadership structure, bringing on Jill Carrick and Jim Doherty as associate directors. We also added the summer English Language Institute STEM program. As many of you probably know, the summer programs have been a long tradition at the upper school campus, as well as the lower school campus. And we did add the International English Language Institute STEM in that year as well. In 2019, Dr. Nerozzi joined us as an associate director. So some of our extracurricular programming, we do have, as I mentioned, the STEM lecture series. Those are typically evening events. We also have STEM Saturdays where we bring various groups onto the campus in order to participate in STEM-based activities. All of those events both the lecture series and the Saturday events, are free and open to the public. We also have a STEM advisory board, and that is comprised of students, faculty, community members. We do partner with other campus departments and clubs. Wherever possible, we bring in other schools and universities. We have lots of fantastic relationships with our local universities and professors, as well as some other professors throughout the country. And whenever possible, we also try to collaborate through the advisory board with industry professionals. A little more about the advisory board. The advisory board is, as I said, it's made up of students, faculty, and community members. This group plans and shapes the STEM events that we hold on campus. Again, we try whenever possible to collaborate with other clubs. Some of the events that we pull together are those STEM Saturdays and the lecture series. We have several annual STEM events. The Summer STEM, which is an opportunity to bring together members of our community to talk about work that they've done within the STEM fields throughout the summers, between the spring and fall of the school year. We have a STEAM Saturday, which we're very excited about. STEAM is introducing the arts into STEM. We have had two STEAM events. The first one featuring the Keystone Mobile Glass Blowing Studio, where we actually brought a mobile blast furnace onto campus and had a glass blowing event on a Saturday. We also then featured an aluminum pour the following year. Every year we have the STEM alumni panel made up of various speakers, of course, all alumni, to talk about the work that they have done in STEM fields. Lower school, we offer a global day of play where we put down our electronic devices and do things with cardboard and other recycled materials in order to make creations of all sorts. But then we do pick up the electronic devices again for Beyond the Hour of Code, where students come onto the lower school campus and learn from pre-kindergarten all the way up through 8th grade, various elements of doing computer coding or programming. So some of the things that we as the STEM leadership and the students involved in STEM do on campus, we love to collaborate with other clubs and departments. We try to partner wherever possible with parents, alumni, other schools, and the colleges and universities, with business and industry professionals. We have the ability to purchase supplies and equipments. We sponsor off-campus trips, as well as assisting in funding other campus clubs. Within our curriculum, at the lower school, which at this time features students from toddler to grade 8, at every grade level, we have at least one unit that engages students in STEM-based learning. I'll highlight just a couple of them. The pre-kindergarten and kindergarten students work with these miniature devices that involve using, in some cases, magnetic or colored tiles. Each of these tiles represent movements for either a virtual or an actual robot. And so they're able to begin to think sequentially in terms of making something move from point A to point B to point C in order to accomplish a task. And it is amazing what students at such a young age are able to pick up and do. And again, they're able to work collaboratively and just engage in learning of all sorts. I'll fast forward to 5th grade, which is the section that I teach. We have two interdisciplinary STEM units. The first one is in the fall. It involves studying geology as well as weather and the water cycle. We look at natural disasters and the processes that are involved in earthquakes occurring, as well as hurricanes, and really any sort of natural disaster. But each of the units includes a robotics challenge. So the students are engaged in doing their own research, following some pre-established parameters that we have for them to follow. And then the culminating activity is a robotics challenge, where each of the stations at a robot table represents some facet of preparing for, responding to, or recovering from a natural disaster. And so they're engaged in some really fantastic hands-on learning. And then we have a spring unit that is titled the Green City Challenge, where we study the infrastructure of a given city look at the way that things are currently done, everything from how fresh water is delivered to how water is treated as it leaves a business or your home. We look at the way that energy is produced. And then we take all of those areas and we look at greener or more earth-friendly ways of generating electricity and handling our resources. And again, that culminates with a robotics challenge. Each one of those challenges representing something having to do with green energy or water management. So there's some fantastic challenges. At the upper school, we also have the Freshman STEM Foundations course that is a required course for all freshmen to take. In their junior and senior years, we have up to 6 different STEM electives available for students to choose from. They're offered every other year, so it's 3 each year. Locomotion, submersibles, and flight would be a fall, winter, and spring course. And then again, the electronics, the digital circuits, and physical computing would again be fall, winter, and spring for a second year. I'm very excited to talk about next the new STEM-STEAM academic concentration. So we'll get to that in a few minutes. In fact, I'll talk about that now. So we have 2 academic concentrations, one in climate science that I'm not sure if you were able to attend one that was featured earlier in the year, one of these SEM talks. Nicole Lewis and Mrs. Rachel Bartran talked about that. They are the chairs for that program. We also have our STEM-STEAM concentration. Both concentrations are intended to follow a model much like a major in college. They're 4-year programs, and they do have required components. There is an academic coursework requirement that does happen quite naturally as students follow naturally their interests in the academic courses that they choose while completing their graduation requirements. In addition to that is an independent work requirement where students engage in, as I mentioned, independent work projects that could range anywhere from a few weeks long to a few months long. That work is sustained over the course of their career at SEM and ultimately should lead to a capstone project, which would be presented in the fall of their senior year. In addition to that, they receive a recognition at graduation with a special transcript designation. For STEM and STEAM, some potential areas are natural and applied sciences, technology, computer science, engineering, art or design, and math. And the 2 images that are featured on here, the image to the left is a 3D printed model rocket that we designed and printed and then had a successful launch. And then the image to the right is the first year of our STEAM Saturday, which was the mobile glass blowing studio. But that's enough for me. So I'll turn it over now to our students because they really have the exciting things to talk about and share with you. So we'll first hear from Dominica. She's a junior and is involved in SRG and some other fantastic projects.
Hi everyone, my name is Dominica and I'm a junior at SEM and I'm involved in SRG, which I've been doing for the past couple years, and I am also currently in AP Bio, and I just joined the new STEM/STEAM concentration, so I'm really excited to do that. And so I'm going to talk about a little bit about the previous project that I did this year. So I just competed at the PJS competition, which is the Pennsylvania Junior Academy of Science. And I competed there with Drew and Paul, who will be speaking later. And we all received first awards, which was really great. And so my project was the effects of antagonists on yeast fermentation. And so basically what my question was what were the acute effects? Like what acute effects do different metal ions have on yeast fermentation? So what I did was I wanted to see, we were learning about yeast in class in AP Bio, and I was really interested on learning more about it and fermentation and different things like that. So I decided for my project to go a little bit deeper and see if different metals have an effect. If you add metals to yeast, will it affect the fermentation rates? Will it decrease? Things like that. And if different metals have different effects. So I did some research, and what I found I found like many different things, but this is what I kind of kept referring back to. So this is a table, and it shows the different levels of like how dangerous or poisonous each metals were. So I decided to pick one from each category. So I decided to do copper from very poisonous, and then from moderately poisonous, I did cobalt, and then from slightly poisonous, I did sodium. The reason I chose these is because they were most easily attainable in the laboratory, and as you can see, a lot of them are kind of they're they're kind of harmful to humans, so it wouldn't have been that great to use them. So these are just some of the pictures from the laboratory. I have some pictures here. So what I did was for my experiment, I did dilution series. So what that means is I diluted the concentration of the metals to see at which concentration, how low I'd have to go before the effect of the metals had no effect at all. So as you can see, this is this picture, the one on the left is the picture of the dilution series for my copper. And on the picture on the right is what I did for the experiment, how I placed. So what I did was I did 3 milliliters of the zero point 0.3 of the yeast concentration. And then I did it with the glucose, 0.3 molar glucose, which is kind of like a food for your yeast so that it can start to undergo fermentation. And then I did a couple like 0.3 molar of my antagonist, which whatever metal I was doing at the time. And then I did about 2 milliliters of oil on top so that no oxygen would get to the yeast. So it would undergo fermentation instead of respiration. And so, as you can see, I had to do 3 trials for each, and I had many of them going at one time, which at sometimes it got a little bit stressful, but it was really cool to see having them all go. It looked very sciencey. So it was really cool about that. And so this is an example of the lab quest. So what I did was I used the rate of fermentation, and then I did the line of best fit just for the part where it was at the most linear part, because it takes the yeast to get once they get into a new environment, it takes them a little while to get situated and get ready. So what you want to do is you want to take it for like the linear part. So as you can see for this one, we had a slope of 0.031268, which would be the rate of fermentation. So here are just my results in the end. So what I ended up having was, as you can see, just as the table predicted, we had the 100 millimolars of copper had the lowest rate of fermentation, and then 100 millimolars of cobalt, which was in like the moderately poisonous, that was like next. And then we had the sodium, which is said was like not poisonous. It came out to exactly the control. And my control was the rate of fermentation without any of the metals acting on it. So it was really great to see these results. And I think that is all. And so thank you. I will pass it off to Paul.
Okay. Hi everyone. It's great to be here tonight. I want to thank Dominica and Mr. Item and Dr. Rosie and everyone for being here tonight. And so really so to introduce myself really quick. So I'm a freshman at Wyoming Seminary Upper School. This is my second year at SEM. I just joined the lower school last year for 8th grade. And I was asked to speak here tonight with you guys because I'm a part of the STEAM concentration. And I also participated with Dominica and Drew in science research group this year. So I know Mr. Item touched briefly upon STEAM and how we're now tying art and STEM and everything together so that students can really focus on that course of academic study. And I feel like SEM really excels above other schools in that program because of the way that they tie everything together and give real life applications. I, for one, had never really been all that interested in science throughout middle school, elementary school, but it was actually when I transferred over to the lower school and took the 8th grade course there that I was able to really see how awesome science was, and it really sparked my interest in it because of the way they tie everything together and show real life applications. So it's not just learning about chemistry, but it's also learning about how chemistry is present in our everyday lives and doing different labs to discuss it. And then that real life application only continues as you go throughout your course of study in the upper school, especially in freshman year, in which we have our STEM course, STEM Foundations. It's not a traditional class in the sense that it's just studying and memorization of chemical formulas or rule or scientific rules. What it really is it's labs and learning how to apply what you learned in the classroom to labs. I see Mrs. Lewis out there in the audience, and she does a great job. She's one of the teachers. Miss Garcia also helps to teach it. So for example, we learn about physics and Newton's laws, but then we apply that by building mini bridges with toothpicks and other materials. And we're going to go ahead and see how Newton's laws apply to that, where our bridges fail, where we could have done better, and how that all ties together. And then I also mentioned about art in the STEAM concentration. So it's not just STEM anymore. We're also adding that A for art. And I'm also studying art with Miss Ayers, who's also in the audience tonight. And what I feel is really special about having art now in the mix is it's not just the science, technology, engineering, and math anymore, obviously. But now that you have that there, you could tie that into your interests. I, for one, have a strong passion for art, and I'm able to tie that into my course of study at SEM. So for the STEAM concentration, we're going to have to do a capstone project. I'm going to be able to potentially tie art in, whether I want to build something for ceramics, if I want to find a way to build an improved spinning wheat pottery wheel. And that could be a capstone project, for example. It's all about going through the scientific method and having your question, figuring out how you're going to solve it. And I feel like that's where STEM really does a great job. They teach us what we're going to need to know in the real world. So I recently had a project with Dr. Narosi that I'm actually going to pull up on screen right now to show you a quick example. So this was, as Dominica shared, this was my science research project. And you can see it on screen. My project was, is it ripe yet? Building a ripometer. So what I did was I went ahead and brought out the engineering skills, and I built a circuit to measure how bananas work. So it was to see if ripeness of fruit can be detected based on that fruit's ability to reflect light. So you go throughout the scientific method, you establish your background research, and then you're going to have to give a presentation and actually educate your audience on your topic, obviously. And it's just like a real world science presentation would be as you would do in a real job. And then so you have to formulate hypothesis, you have to go about and formulate procedure once you have your question. Here you can see how I built my circuit. And then here's what my circuit actually looked like. And then I had to test my circuit, go about that, measure the resistance based on how much light the fruit was able to reflect. And then I had to go ahead and actually measure the banana, as you could see on screen over there to the right. And so what basically happens is I shined the light on it. It would come back after I did all the circuitry and into a special piece called a photoresistor, and that would give a measure of how much light the banana was reflecting back onto my circuit. And then I was able to read it on the multimeter. Here's what my banana looked like throughout its process. And then you get your final results and you get to analyze them, see what you could have done better, see what you did right. And so it's really the application, as I've stressed a lot throughout this. And I really feel like that's what sparked my passion for STEM and STEAM at the upper school. And I really think it's a great program and it's continuing to grow.
Thank you, Paul. That's absolutely fantastic. And now we're going to hand things over to Pat to talk about his 3D printing.
Hey guys, I'm Pat. I'm a junior and I'm from Thailand. Today I want to talk about my program, not my program. It's a SolidWorks program. Wait, I'll share my screen. My bad. All right. Okay. So SolidWorks. What is SolidWorks? SolidWorks is a solid modeling 3D design, and with the help of engineering. Basically, it means that we're it's a 3D modeling program which uses the help of engineering and physics. Okay. So SolidWorks. Okay, I'm a bit nervous. Let me start over.
You're doing great.
My bad. Okay, so SolidWorks is a engineering 3D modeling program with in 3D printing, and I would like to talk about SolidWorks. I am very passionate about SolidWorks. That in the spring break, I actually made a 3D prosthetic arm that in the SolidWorks model, and I printed it out, and I have it here to show you guys. So this is a 3D, it's a three finger with the socket. It's not done yet, but when it's done, I'm putting Arduino in this so it could actually move. Yeah, and okay. Okay. Why do we want this program in the in our STEAM program? So SolidWorks, it requires physics, technology, and art, and engineering and math. And I'm trying to bring this to the campus and try to have a class with the SolidWorks with the help of Mrs. Ayers and the professor in the Keystone College, and John Idams. John Idam. Yep. Thank you. I'm sorry. I'm very nervous.
No, that's perfect. So I would like to add to that. I don't know. Are you able to hear me at this point?
Yes, we can hear you.
Okay, perfect. So I just wanted to add to that with the STEAM program. The faculty group of advisors that we have, it's our current STEM leadership, who I talked about earlier with it being Jim Doherty, Jill Carrick, Dr. Norozi, but also Mr. Mark Weber, who is a part of our Zoom tonight, as well as Ms. Colleen Ayers. They are both two advisors that are part of this program that we're just delighted to be partnering together, to be pulling in all of these pieces to represent each of the letters in STEAM. And as you can see from Pat's project, the integration of art into STEM is just crucial when you look at how to design something like a robotic hand. So thank you, Pat, for sharing that with us. And thank you to all of our student presenters. So you guys are a fantastic representation of our program and what we're trying to do. With that, I'm going to hand it over to Dr. Norozi, who's going to talk about the SRG, or the Science Research Group program. And then we'd be delighted to open it up for any questions that you might have.
All right. Hi. Thank you all for coming. I'm going to share a screen. I didn't know I was going to talk today, so we'll see how this goes. This is a presentation I'm doing about SRG for other purposes. It's here mostly to help guide me in what I say. There I am years ago, when I was 18, roughly the same age as the students who are, seniors at our school. And when I was an undergrad and I was that young, I became involved in research in the freshman year, which in 1980 was an unusual thing to do. And it was a totally transformative experience. And then since that time to the end of my graduate school years, and then afterwards when I worked as a postdoc, I had been in research all those years, something like 15 years. And when I was hired at seminary, I wanted to bring research experience to the high school level. And this was in 1996, 1997. So about 16 years before the start of the STEM program, and way before STEM as an acronym was actually an acronym. And so it harkens back. So this idea of research is an old one. It's around for a very long time. And it's very different to do science than it is to talk about science. And so much like you can read many books and become a critic of literature, it's very different to actually be a writer. And that's exactly the sort of analogy that goes on here. Courses are fundamental for developing and understanding, but getting some hands-on work where you're independent, you're autonomous, and you're in charge of the project is really very important, because that builds skills that you don't, even in a project-based lab in the classroom. I'm not going to read all of these things, but really it's the integration of this freedom along with the focus of it being hands-on discovery that makes doing a research project so important to the development of someone's creativity. The idea behind SRG is that just as you wouldn't say to an athlete that oh, you want to be really good in field hockey, but why don't you just take some PE classes, and then when you go to college, become an athlete and become a member of the team. Instead, you would say, no, we want you to start now and be a field hockey player now. And that's the idea that was the founding idea for SRG, and the continuing idea in the STEM program and the STEM concentration, that doing is a very important thing. So that's where it has its roots, quite a long time ago. I'm not going to go through all of these things. There are a lot of, let me do benefits. There are a lot of benefits to the HSRE is an acronym for high school research experience, which Debbie and I are coining, by the way. And it has to do with what are the gains out of this? And these gains are multiple, but really it's participation and retention in STEM disciplines. And then also increases in knowledge and practices. And you kind of would expect those two kind of things to happen if people are become more intensely engaged in something. But the part that I want to point out here is over in the corner, right-hand side, integrate students into STEM culture. And that's something that the STEM program and the STEM concentration are aimed at doing, which is to take this idea of science research group and the other aspects of STEM that were already talked about, and to pull them together and create an environment in which we support the kids more fully. And so we've been doing a great job actually up until now. And the hope is that the STEAM program will be able to unify the kids in a way that in the absence of the concentration wasn't as easy to manage. So that's where we're going with this piece here. All of the literature in education that has to do with research experience on the college level or the high school level suggests that this integration into culture is a key pin in somebody remaining interested in the discipline and continuing on to have a career in science. So there's a lot more that I can say. You see the whole bunch of slides here. What I want to do though is say there's been a number of kids that have come through SRG, and they do a variety of different projects. And so you saw some of those projects today with Dominica and Paul, and they did a great job sharing their work, and with Pat in the STEAM section. And so, it takes some fostering and it takes some intense work. It works very well to advance skills and allow students to progress on the college level at a rate faster than they would if they didn't have such an experience. And so our grads, our alumni tell us that that's definitely the case. And so that's something that we're looking forward to. For the kids who are here, just the path through this is multiple. And this is a simple chart. These are students, 5 different students, and the titles of their work and what they did. And they come in all kinds of ways, right? Here's one person who came in as a sophomore and did just one project and was done. Here's one who came in as a junior, worked again as a senior, did kind of complicated biochemical stuff. And then so on. We have somebody who worked in computers, and then we have somebody who did a variety of different things and was involved for 4 years, and somebody who took one project and did the same project and then did iterations of that project with time. And so for the listeners and also for the students, there's lots of different ways to go through project-based learning in independent learning. And sometimes you might start with something. I remember the student really didn't like growing plants. And so they switched to microbes. And then after having taken some more chemistry, they moved on to protein isolation. So we're not pigeonholing students into one particular area. We want to encourage them to explore and find things that are interesting to them, and then to follow up on a lead. And so a project that has iterations like this one is fantastic if you know that that's the thing that you really want to stay with and be with for 3 years. But there's lots of different ways to explore. And so there's a considerable flexibility within the program.